Thank you, Shai. Thanks for coming. Okay, I'll talk about modern challenges in learning theory. So my research is focused on theoretical aspects of machine learning and specifically theoretical aspects of generalization. So what is generalization? Generalization is maybe kind of the defining property of machine learning, the ability of a learning algorithm to get as an input a finite training data, process it in some way that we call training, and then output some prediction function, which if it performs well on new data that's not given to us in the training data, this is what we call generalization. Good. So as I said, I focus on the theoretical perspective of generalization, and specifically my research is guided by kind of the following questions. So first, the question is, what can we learn? Can we characterize in some precise mathematical way the types of problems, the learning problems that admit generalization? The kind of complementary question is, how can we do that efficiently? What are algorithmic approaches to that? And finally, what are the limitations and trade-offs between different constraints to the problem? For example, how much data is needed versus how much runtime, etc. So I like to think about generalization in machine learning kind of categorized by the types of problems, and specifically by the way that the algorithm interacts with the environment. So let's give this kind of very rough categorization according to interactivity level. So kind of the first really basic, most fundamental layer here is statistical learning or supervised learning, where I have some distribution over the data and I'm getting a fixed batch of training data. So you can think of problems like classification, regression, etc. Adding another level of interactivity between the algorithm and the environment, you can think of sequential types of problems, online learning, online classification, online regression, where the data points come one by one in sort of a streaming fashion. And we want to make predictions on the fly. So here we have different notions of generalization that we want to think about. And sort of the last layer of interactivity is still a sequential type of learning, but where the prediction of the algorithm also changes the environment and affects the observation that the algorithm will see in the following round. So it's usually that you have problems in robotics, reinforcement learning, control. And that's another different notion of generalization that we can think. So just to give an overview of the types of work that I've done in these different categories. So in the context of statistical learning, I've worked a lot on multiclass classification and specifically on sample complexity bound, essentially saying how much data is needed to learn. I've worked a lot on efficient algorithms given Oracle access to weak oracles that are weak in some sense. This is typically called boosting theory, and I'll talk about that later in this talk. And it works on multi-objective learning, where we have different criteria that we want to satisfy beyond the kind of standard classification loss or standard loss. In the context of sequential learning, I've worked on, again, boosting algorithms, but now in online classification and online regression. I've worked on the multi-unbounded problem, both hardness results and algorithms. And in interactive decision-making, I've worked on algorithms for online control and reinforcement learning under various relaxations. So kind of a different perspective of these works, I want to sort of give this other categorization where a lot of my work is focused on the information or statistical side of things, essentially saying how much data is needed to learn. And the complementary aspect of that is the algorithmic or computation side, which is designing, developing algorithms, maybe under some relaxation. I've worked on trade-offs between, again, the different constraints, time, data, maybe memory, or other resources that we have. And some works on alignment or multi-objective learning, where we have kind of different criteria, or we want to design an algorithm to be better suited to a user-desired behavior. So that's my work. I won't talk about most of that today. I will focus on these two works. First on, so from the information side of things, a characterization of multiclass learning. And then from the computation side or algorithmic side of things, I'll talk about an efficient algorithm, multiclass boosting. And then towards the end of the talk, I'll also talk about sequential learning and specifically the problem of multi-unboundeds. Okay, so the outline of the talk, as I already said, most of the talk will focus on multi-class classification. first answering the question of what can we learn. So giving a characterization of the types of problems that admit generalization, and then describing a boosting algorithm. Then towards the end of the talk, I'll talk about sequential learning and bounding the number of queries that are needed to learn in this model. Good. So let's start with the first part of the talk, characterization of multiclass pattern learning. Okay, so before I go into that, I want to give this kind of high-level motivation of why do we want to study multiclass classification. So you can think of learning theory landscape as sort of a spectrum, where on one end of the spectrum, we have kind of the classic binary classification, pack learning, statistical learning, for those who are familiar. And this was studied in the 80s, very well studied, very well understood. We have a lot of kind of tools that are developed for this setting. On the other end of the spectrum, you can think of your favorite problem in learning theory that we don't really understand as well, maybe generative models or something else. And we want to kind of, we know that a lot of the tools don't really work in this more general setting. We would like to understand that better. So the original kind of classical statistical learning setting is pretty far mathematically from these more practical settings. But what I want to point out is that in a setting that is much closer to the original one, which is multi-class classification, where we basically keep the entire formulation but modify the number of labels. Instead of having just 2 labels, we have many. Already a lot of the tools or ideas break down or don't generalize as well. So we want to focus on this part of the spectrum and understand that better, maybe in the hopes that it will give us more insights for other practical settings. Good, so let's zoom in on this part of the spectrum. So what I mean here, and I'm just throwing up some names here, some terms, and I'll define some of them later. So here we have tools like VC theory, which is essentially telling us how much data is needed to learn. We have simple algorithmic approaches like empirical risk minimization, boosting theory, ideas like uniform conversions, and in one way or another, they don't generalize or don't work as well in the multi-class setting where I have many labels. So that's kind of the motivation. And now let's dive into the setting and the definitions. And to do that, we'll start with binary classification. Okay, so binary classification, I'm sure you all know, it's a very standard problem. So we're given as input a bunch of classified data points, X and Y, where X can be images of cats and dogs, and Y can be, and Y it's the label, so 0 if it's a cat and 1 if it's a dog, for example. Then we get a new image, we want to classify it correctly. So more formally, I'm thinking of a learning problem as a distribution V over the domain X and the label space Y, where Y here is just a set of 0 and 1. Later on, we'll have more labels. The learning problem is given a training set of M labeled examples, drawn IID from the distribution. We want to return a classifier, which is just a function mapping X to Y. The goal is to as I said, to correctly classify a fresh point also sampled from the same distribution, and we measure the error of the classifier H simply by the probability of it being wrong over this distribution. Okay, so this is a hard problem, so we typically add an assumption, and the standard assumption in this context that we add is as follows. So we assume that there is a hypothesis class H, simply a set of functions mapping X to Y. We assume it's known to the algorithm, and such that the unknown distribution D that we're trying to learn is realizable with respect to the class. Realizable just means that the true kind of ground truth classifier is somewhere in this class, meaning there's some H star that has a 0 error. That's the realizable setting. The agnostic setting, where we remove that assumption, is also relevant, and we also pretty much all the results that I'm going to describe today have a version in the agnostic setting, but we'll focus on the realizable case.
Nataly,
yes.
do you also assume that the classes are balanced? Because your error model, just, if the classes are imbalanced, if you can very easily get a good error, right? Like if, for example, most of the samples are 0, then you always predict 0, and your probability will be great.
I'm not. That is true. I'm not making any assumptions. We'll see how we can characterize that.
Except the samples are from the distribution. You assume that the samples are from the distribution, so then it's different. Still, you get the samples from it.
Good. So this is a very classic setting known as the PAC learning setting, probably approximately correct, formalized by somewhat independently by both Vapnik and Chervonenkis in 68 and Valiant in 84. So now I want to add a definition. So I want to define for a class of functions H, what does it mean for it to be PAC learnable? So we say that the class H is PAC learnable if there exists some learning algorithm A, so that for every realizable distribution D and error parameter epsilon between 0 and 1, given a training set of M of epsilon examples drawn IID from this distribution, I want the algorithm to return a classifier H with an expected error of at most epsilon with respect to the same distribution. And for those who are familiar with the definition with the high probability, I'm removing that parameter here. I'm just thinking of expected error. Good. Questions about the definition? Okay. A key property that we care about here is this M of epsilon. That's the sample complexity of the algorithm, sample complexity of the class. It's how many examples we need as a function of epsilon to get error most times. So obviously, I want this to be as small as possible. Good. So now that we have this definition, kind of a basic question that comes up in this context is which classes H are learnable? Which classes even satisfy this definition? And if so, how? What will be the algorithm that we can apply in order to learn? So for those who are not familiar with this classic theory, it may be surprising that there's a simple answer to this question. I want to describe the answer to you, and then we'll describe the challenges of extending it to the multi-class case, and how do we do that. Okay. So in order to answer this question, I want to just give this representation of a class that would be useful for us. So I want to think of a hypothesis class H as simply a set of these binary functions where kind of the columns here corresponds to the points in the domain, like the images of cats and dogs, right? And the rows are the hypotheses, which I'm just thinking of as binary vectors, possibly infinite binary vectors. Okay, now I want to define a property of this class that is called the VC dimension. The VC dimension, we first let's think of restrictions of the class to certain columns in the matrix. So I'm thinking of a restriction of the class to, let's say, columns 2 and 4 by taking all the possible patterns of functions in the class over these two columns. So now we can define the dimension. The VC dimension, Vapnik Chervonenkis dimension, is simply the largest number of columns D, data points D, such that when restricting the class to those D columns, we get the complete D-dimensional Boolean cube. So all 2 to the D combinations. So specifically in this case, we get all these 4 patterns. Questions about the definition? So now let's describe the characterization. So we get what is called the fundamental theorem of PAC learning or fundamental theorem of statistical learning. And this is due to Vapnik and Chervonenkis from 74 and Bloomer et al. From 89. And it says that if a class H is PAC learnable, if and only if its VC dimension is finite. Not only that, we also get kind of a characterization of the optimal sample complexity. So this property M of epsilon, we can say it scales like D over epsilon, where D is the VC dimension. Good. So VC dimension was kind of born in learning theory, but it also has connections to many other areas like discrete and computational geometry, complexity theory, combinatorics, etc. It's kind of a very wonderful, tool and theory that is very general, but unfortunately does not. It's very tailored to the case where we have only 2 labels. So what happens when you have more than 2 labels? How do we generalize all of these ideas? So that's what we're going to focus on. Before that, I just want to quickly talk about the algorithmic approach. So how to learn, I just told you how many samples are needed, but what about the algorithm? So we know that the VC dimension tells us how much data is needed. We also get a simple algorithmic principle called the empirical risk minimization, or ARM. Very intuitive. It just you get a training data, just pick any hypothesis in your class that perfectly fits the data. And ARM tells us that this will be a good choice. It will also generalize. Good. Unfortunately, both of these kind of don't generalize to the multiclass. So we don't have the dimension, and we don't have the ARM principle. We want to understand these. So let's start with generalizing the VC dimension. What happens? Okay, what's the multiclass setting? It's very, very natural. Imagine we still have the problem of classification. We just have many, many labels. So here, maybe you notice that the label space is not bounded, so you can think of the natural numbers, or any set that I don't assume an a priori bound on. And kind of the main challenge to this problem is that when I have really, really large label spaces, I have extremely large label spaces, I don't want my problem to depend on the number of labels. Good. Okay, so what did people do in this context? Already in the late 80s, a lot of people were thinking about it, and Tarjan initiated the study of multi-class pack learning. And among other parameters, he identified a key combinatorial dimension that we now call the Tarjan dimension of a class. And it does what we want, like it generalizes the VC dimension, and it gives us bounds on the sample complexities, parameter m of epsilon. So we get bounds that are similar to the VC bounds, except now the upper bound scales with log y. In particular, when y is infinite, this becomes a vacuous theorem. So the question remains, what happens when we have unbounded label spaces? Does the Tarjan characterize learnability? Maybe another dimension. What is the truth? So in one way or another, this question was asked. Essentially the question of, is pack learnability equivalent to the finiteness of the Tarjan dimension? And this was asked starting from Tarjan in '89 and in later works as well. And then in a joint work with Dino, Carmon, Moran, and Yudayev in 2022, we answer this negatively in a strong sense. So we show that the Tarjan does not characterize learnability. I'll explain that later. But then we show that a different dimension that we call the DS dimension does characterize learnability. We call it the DS dimension after a paper by Danieli and Schwartz from 2014, where they kind of proposed this, it's not kind of the main focus of their paper, but they proposed this dimension and conjectured maybe the true one. We proved that this was indeed. Okay, so I wanted to find the DS dimension and describe the results. Before we do that, let's talk about connection between learning and graphs. So remember this kind of matrix representation of a hypothesis class that I gave you before. We can also represent this as a graph, a Hamming graph, where the nodes of the graph correspond to the rows of the matrix, the hypotheses in my class. And I have an edge between two hypotheses if they disagree on exactly one coordinate, on one data point, right? So this is the Hamming graph. Let me define a more general notion instead of defining this. So we want to generalize this idea. We define what we call a Hamming hypergraph, also known as the one inclusion graph. Okay, so let's define it. Let's say that we have exactly n data points. It's finite. We have n kind of columns in our matrix. The graph that we define, the hypergraph, the nodes of the hypergraph would be the vectors, the binary vectors, the hypotheses in my class, and the hyperedges are going to be as follows. For each hyperedge, I have a coordinate I between 1 and n, such that all hypotheses in the hyperedge differ only in that coordinate. They agree on all other coordinates and differ in the I coordinates. Okay, so this is maybe a confusing definition. Let's see an example. It will be much more clear, hopefully. So here's the example that I have. So here I have a class. It's not a binary class, right? I have different labels. I have 3 data points, x1 over x3. And let's see how it corresponds to this Hamming hypergraph. So the first node, H1, corresponds to this vertex in the graph. And these two vertices, H1 and H2, are connected by an edge because they disagree only on the green coordinate. They agree on all other coordinates. Another example is these three nodes, H1, H3, and H4, are connected by this hyperedge because they agree on all coordinates except the blue coordinate, middle one. Definition clear?
So it has both the hyperedges and the normal humming edges?
So it has the maximal one. So I don't have the kind of, there's no edge between H1 and H4, there's the hyper. I'm only thinking of the maximal one.
Okay. Mhm.
Good. Okay. Okay, now our goal is to generalize the VC dimension, right? So let's see how we can do that. But the important idea is generalizing the property of Boolean cubes. So remember the VC dimension was related to Boolean cubes, and a d-dimensional Boolean cube is simply a d-regular Hamming graph. So these are examples of d-regular Hamming graphs. These are a two-dimensional cube, a three-dimensional cube, right? So this is the Hamming graph. We generalize this by defining the notion of a d-dimensional pseudocube. And a pseudocube is over a Hamming graph of the coordinates is any d-regular graph. Any d-regular graph over d coordinates. So you can see examples of these two-dimensional, three-dimensional pseudocubes that are very different from the cube-like structure. So again, the key property is that all nodes have exactly d edges. Any questions about the definition? Okay, good. So now we can define the notion of the ds dimension. And the ds dimension is the largest number d, such that when largest number of data points d, such that when restricting the class to those d data points, constructing the Hamming graph over them, you get a d-dimensional pseudocube. Contains a d-dimensional pseudocube. So maybe you can see that if there's only two labels, this is exactly analogous to the VC dimension. You get the Hamming graph and a Boolean. Yes. Yeah.
I wonder how is this related to the pseudo? I know like pseudo dimension is another generalization of VC dimension.
Right. Yeah.
How is this related to this DS or previous one?
The Nataly dimension is actually a good question. I'll talk about that in a bit. So we have a result on the connection between them, which is not obvious. But for the pseudo dimension, I actually don't remember the definition. But I think it was not a contestant to be the kind of there were gaps between the Nataly and the pseudo dimension. So kind of the main conjecture was about the Nataly. I don't quite remember the definition of the pseudo. But yeah, the Nataly dimension, we were thinking about the difference between them, and that's very non-trivial. And how are they related? Okay. Good. So now let me describe the main results with respect to the DS dimension. So what we show in this work that a class H is back learnable if and only if its DS dimension is finite. Good. What about the sample complexity? So we show that the sample complexity M of epsilon, that we have the lower bound of d over epsilon. That was kind of implied by the work of Nataly and Schwartz, very similar to the bound that we have from the VC and from the Nataly. The upper bound is kind of where the main challenge lies, and we get an upper bound of d to the 1.5 over epsilon. And importantly, there's no log y, there's no dependency on the label space, which can be in particular infinite. Good. So I'm not going to talk about the proof. I will just say that the proof is there's many different components. It uses many tools from both learning theory, combinatorics. So we have sample compression, shifting, boosting, ERM, transactive learning. So these are all kind of classical tools that we use in the proof in non-trivial way. But we also have kind of a novel technique that we define in this work that I do want to describe because it will also be useful for the next part of the talk. So this technique is, we call this list pack learning. So I'll describe that now and how it's used in the proof. Okay, so what is list pack learning? It's a relaxation of pack learning, very kind of, I don't know, intuitive relaxation, where we still want to classify our data, but now instead of requiring the algorithm to return exactly the correct label, we allow it to return a short list that is likely to contain the true label. So the size of the list is going to be a parameter, k, and then we can define this k list learning. It's also known as top k classifications. People thought about it in more kind of empirical context. Okay, so how is this notion used in our proof? I'm going to give a very rough overview of the proof, essentially only talking about the connection to list learning, but obviously, hiding a lot of the details. We start from the assumption that the DS dimension is finite. We're then able to use that property to construct a list learner for our class H, where the size of the list is going to scale with the parameter D. Once we have that list learner, we're able to apply it to our class and kind of get an effective proxy class with a reduced label space. So if we initially had a label space Y, which was maybe infinite, we're now able to get a reduced label space Y prime, where we do that by mapping. So kind of the new label space would be the size of the list, and the true label would now be the position of the original true label within the list. Once we have that, we essentially got a proxy class with reduced label spaces. We're able to apply other techniques to learn that reduced label space class. Okay, fine.
So, question. So, if you have a number of examples, then automatically you have the finite labeling, because it's only the label that appears on the examples. So why it's not? I mean, assuming you have a finite number of examples, the labels is finite because it's only the labels that appear in the example.
Predict examples that were not given to you in the training data, right? Yeah.
How does the label size affect your previous result with the DS dimension? Oh, okay.
So the result with the DS dimension is entirely independent of the size of the label space. With an Nataly bound, you get the log Y in the upper bound.
Okay.
Good. Okay. Let me point out or mention two open questions in this context. So the first one, maybe you noticed, when I showed you the sample complexity bound, there was a gap between the lower bound and the upper bound with the polynomial gap. The conjecture is that we have a bound of D over epsilon, similarly to the VC dimension, but that is still open. Yes.
Related to the first question, do you have, let's say, values of the DS dimension for, let's say, I don't know, multiclass logistic regression?
Multiclass. So you need to come up with a particular class of problems. Yeah, and then we can carry. But it's not always obvious, but for some classes we do have.
Okay.
Okay. Yeah.
And what about the classifying what you can list learn? Is it the same criteria?
Great question. I'll talk about that a little bit later, but there were some follow-up works that kind of extended the DS dimension to, if that's your question, like how many examples you need to list learn. Yeah, there were extensions of the DS dimension to that setting. Yeah.
Okay.
Okay. Good. So another thing that I want to mention is the algorithmic approach. So kind of alluded to the proof of the upper bound with many different components, very complex. So it would be interesting to get a kind of a simplified approach, analogous to what we have in the binary case, kind of ERM principle. We don't have anything near that in multiclass learning. Okay. I want to mention something related to Michal's question before. What about the Nataly dimension? So there was this conjecture about the Nataly dimension. People thought about that for many years. So we proved that the DS dimension is the true one, but how is this related to Nataly? Maybe they are kind of equivalent, maybe they scale together. So this was not clear to us when we were thinking about this problem. But then we show that we eventually show that there is a non-learnable class H with infinite ds dimension, so infinitely large pseudocubes, such that in the Targum dimension is kept just 1. So the gap can be very, very large. The way we show this result is by identifying a connection between learning theory and algebraic topology. And then the proof is based on this deep and involved construction in algebraic topology by Mshkevitz and Shwiatkowski in 2003. Okay, good. So that's, I think, all I wanted to say here. So kind of to summarize this part on multiclass spec learning, I showed you there is a characterization of learnability via the DS dimension. In a more recent work, we also have a fine-grained characterization of learnability, kind of a more refined notion of learning than the original or classic spec learning. And we do that by a family of combinatorial dimensions and kind of a similar spirit to the DS dimension, etc. In both of these works, we don't have algorithms. So these are kind of involved constructions. They're not efficient and they're not simple. So for the next part of the talk, I want to focus on an algorithmic approach to this problem of multiclass learning. Okay, we're moving on to the next part. How can we efficiently learn? The algorithmic approach that I want to describe is boosting. So for those who are not familiar, let me describe what boosting is. So let's say, we have a learning problem, right? And we don't have an algorithm. So it's a challenging problem. We don't have an algorithm. Let's say we work really hard and we develop some sort of algorithm for our problem and we test it out and it's not very good. It has a mediocre accuracy. What can we do? Can we somehow boost its accuracy to get a strong or to get a good learner for our problem? And so this is kind of a classic question. It turns out that for binary classification, the answer is yes. And moreover, it can even improve weak learners to have arbitrarily good accuracy. But by weak, I mean doing slightly better than random guessing. So let's say you just flip a coin and predict according to that. If you do slightly better than that, you can already boost your algorithm to have arbitrarily good accuracy. So this is a long line of work initiated in the late 80s by Kearns, originally asked the question, for Shapiri. It has since been this kind of fundamental approach in machine learning with both, very huge practical success as well as this kind of solid theoretical foundation. So let me first define it a bit more formally, and then we'll talk about extending it to the multiclass case and what goes wrong. Okay, so what's the assumption? Similarly to the pack definition, we have an algorithm, we have a class H and a gamma weak learner, where gamma is a parameter between 0 and 1. We say that a weak learner is, an algorithm is a weak learner for the class if for every distribution, when given some samples, it returns something that does slightly better than half, random guessing. So we're given m examples, we return something that has correctness at least half those scans. What's the main result? This is due to Freund and Shapiri, kind of a long line of works by both Freund and Shapiri. They show that there's an equivalence between a class having a gamma weak learner for some gamma bigger than 0, and the class being strongly packed learnable. And this equivalence is also algorithmic. So if I have Oracle access to a weak learner, I can efficiently improve it and get a packed learner. Good. So that's kind of the classical theory here. What do we want to do? What happens when we're thinking about the multiclass case? Okay, so first we need to define a weak learner. What's a weak learner in multiclass learning? So the intuition was, okay, we want our Oracle to do slightly better than random guessing, right? And slightly better than random was half plus gamma. Okay, so let's define the multiclass version of that. So instead of tossing a coin, we'll toss a dice. And will be better than 1 over y plus gamma. This, unfortunately, is provably too weak. So there are simple constructions that for which you have algorithms that satisfy this definition, but you cannot boost them. There's no way to improve or get any strong learner for this class. There are also other notions that people thought about, but they're all kind of too weak or very complex, require assumptions with respect to these tailored loss functions that we don't want to assume. So kind of the two natural questions that come up here is first, what is a good weak learning rule? What is a good assumption, a kind of simple enough assumption to make? And then once we have that, how can we efficiently boost that? And by efficient, again, I'm thinking of huge label spaces or even infinite label spaces, and I want the running time and the sample complexity to be ideally independent of the number of labels. Okay. So now I want to describe our results. So we define a new notion of weak learning that is, hopefully you agree, is a simple one. And this is joint work with Nataly, Shai, and Chervonenkis. Okay, so what is the assumption that we're making? First, let's recall the weak learning assumption that I just told you was too weak. This assumption that our correctness is at least 1 over y plus gamma. I'll show you how to tweak it a little bit, and this tweak will be already sufficient for boosting. So what's the tweak that we need to make? What if somebody gave you a hint function? That's a function that contains a true label. You don't know which one it is, but contains a true label. Can you then do better than random guessing over that list? Okay, so that's the kind of addition that we're adding to our assumption. So formally, let's define a BRG learner, where BRG stands for better than random guess. I again have this parameter gamma between 0 and 1. And I said an algorithm is a BRG weak learner if for every distribution, every integer k, and every good hint function, where a hint function gets as an input data point and returns a list of k labels, and we say that it's good if it contains a true label. If for every such hint function, the algorithm returns some classifier that is better than random guessing over that list. So at least 1 over k plus gamma. I require this for every k. Importantly, I'm not requiring that the hint function is good or anything. I'm just saying if somebody gave me a list function and it happens to be good, then I want to do well in this sense. So that's the assumption that we're making. Yes.
So for each hint function, you have you draw something from the distribution, and the hint gives. Okay, sorry, I understand.
The hint is a mapping from all data points.
From all data points, each data point gives a different.
Exactly.
Okay.
Yes.
So what happens here? K equals 1. So that's basically the hint function becomes the grand truth.
Yes.
And then what do we get?
Well, if the hint function is 1, then it's not a hint. It's really the answer, right?
Yes, but you're supposed to. Your algorithm is supposed to apply to this k.
So think of k bigger than 2. If k equals 2, this is exactly the binary weak learning condition, right? It's half plus gamma.
Yeah.
Right. More questions?
Maybe just for the notations here, where does n appears here? In the,
Oh, it's just given to the algorithm. Yeah. It's the important part is the guarantee of the function and the k, the parameter k. Sorry. The parameter k, which is the size of the list that appears in the guarantee.
So the definition is for k greater than 2?
Yeah.
Greater or equal.
Yeah.
Greater or equal.
Thanks. More questions? Okay. Now I want to describe the algorithm. So how are we using that assumption? Okay, so I'm just going to describe it from a high level. Let's say that we have a training set of S of M examples, and I want to only use that weak learner assumption and get some sort of predictor that is simple so that we can get generalization properties and achieve 0 errors. That's going to be the goal. We want to get exactly 0 error over the training data. So what's the description of the algorithm? In the first round, I don't have any hint function, right? I'm not assuming access to any of these hint functions. I need to construct them in my algorithm. So what I'm going to do in the first round, I'm just going to feed the weak learner with the trivial hint. The trivial hint would just be all possible labels. the true label is somewhere here in all possible limits. So we're feeding that to the weak learner, and we get some response, some classifier. What we show is that in each round,
So if K was finite, what was the definition?
Yes, so K was finite, but I didn't mention the caveat. So we also assume that for infinite hint functions, kind of the trivial one, I just want correctness of instead of 1 over K plus gamma, just bigger than gamma. Just bigger. Good, thank you. Okay, so then we're able to show, and this kind of, I'm using this as a black box here, but we're able to use the weak learning guarantee plus the multiplicative weight algorithm. And we prove that we can identify some wrong labels. So labels that are for each data point are wrong, are definitely not the right answer. Once we identify those, we remove them. By removing them, we kind of shorten the hints. So we constructed a better hint function. We again repeat this. So we have a shorter list, we feed it to the weak learner, we find more wrong labels, and so on and so forth. Eventually, we're able to reach a hint size, a list size of exactly 1. Once we have a hint size of exactly 1, that's already a classifier, and we're done. What's interesting or maybe surprising here, we're able to do that with only 1 over gamma rounds. So even though, so this is kind of an independent, number of rounds is independent of the number of labels, and we are still able to get to reduce the list all the way to 1. Yes.
How do you go for infinite finite?
So that's part of the algorithm. So what actually happens here is in the first round, we're shrinking the list size to roughly 1 over gamma, and then we can remove at least 1 in each following round. Yeah.
The binary case, the dependence on gamma is exponential. So do you know it?
Exponential?
There's this e to the minus gamma t or this thing like.
No, the number of rounds is not. It's similar. It's not.
Right.
More questions?
Do you assume some independence between the rounds, or I mean the classifier? You give different things. You assume independence before, or
No. So what actually happens? We have to fix training data. We define a distribution over the training data. We sample fresh samples and get from that. But the goal is to get 0 error only over that fixed training data, and then sample progression arguments. We can show generalization.
So in a sense, you assume that you can find all the heavyweight elements. There are only 1 over gamma elements of weight gamma, not weight, probability mass. And so it's like, again, it's a list coordinates. Right, you find the list that contains, no?
there is no assumption of heavyweights.
No, but I mean, if you feed it at the beginning with a trivial hint, and you find an element that has probability mass gamma, then you can just repeat it and find all the elements with probability mass.
So what do you mean by elements? Do you mean like the label?
Yeah.
Not sure. No, so I could be predicting labels that have not appeared in my training data at all.
Yeah, but you find all the heaviness elements.
Yeah, I'm not sure.
You can find all of them, no?
There is no probability distribution, right? Sort of, you're thinking about it incorrectly because you're thinking about the correct thing. There is no probability distribution over the y's. You're just thinking there's x, y coming from a joint distribution.
Yeah, but the assumption that you can find an element, like a correct element with probability at least gamma, I think it's not exactly, but okay.
Question? Which number?
So nothing about efficiency, right?
Sorry?
You don't care about efficiency.
So I do. Let me just talk about.
I mean, the description of H function going to be efficient. This H hint function going to L function, whatever. This L function.
Like the representation of the list function, or sorry?
The implementation. I mean, eventually you need to access right? I mean, getting the learner get access to the query function, to the hint function.
Right.
So the hint function, the way it's
Right.
described, doesn't seem to be efficient.
Right. No, I am assuming that's kind of a free.
So when you use it, you're going to give an efficient implementation of the link function. And eventually, you want to use it to learn something, right?
Yeah, yeah.
Or just you want to use it for application to learn some group, some class, or just if you have these settings, you can do something.
Yeah, if I'm not. I don't have a specific class that I'm.
So
Right?
don't have. Just if you have this, if you happen to have this link function, then you're fine.
But again, I'm only constructing.
Yeah,
them. Yeah, I don't assume I have them. Right? I'm constructing them in the algorithm.
But you assume you have such learners given access to any link function, whatever link function, efficient, inefficient, you still manage to do the task.
Yes, that's the assumption.
It makes sense.
So it could be, it's analogous kind of to the binary case. Does it make sense of the binary case, right? So,
What is the binary case?
so again, the binary case, let's go back to this. So in the binary case, I only have two labels, and I'm assuming that for every distribution, I can find some function that is better than half plus gamma. That's also not trivial to assume that that's efficient, but that's an assumption that seems to be useful in practice. Well, it's kind of
So that's what I was asking in the beginning.
Yeah.
So in practice, you can use this your learning to achieve something, even like it's for some specific classes. You manage to get an efficient.
We didn't try that. So with this particular algorithm and assumption, we did not try that. Empirically. Yeah.
But the data set is finite, so it's efficiently representable.
No, still to round because it waits on the positive plus, right?
No,
No.
no, an algorithm is not efficient, but the hint is the algorithm.
Okay.
The hint is
All right.
The hint is efficient. Right, the hint.
Findings.
Function
Function.
data set.
Okay, let me continue. Okay. So just to describe the main results, so we show that if I have an oracle access to this weak learner that I defined, that using the sample complexity 1/gamma cubed epsilon, we get a boosting algorithm that outputs a classifier H bar, such that it has epsilon error over the distribution. So both the sample complexity and the number of rounds in the algorithm is polynomial in 1/gamma, and specifically it's entirely dependent of the number of labels. So in that sense, it's efficient. Okay.
Thanks.
By the way, so
binary.
Yes.
Binary times gamma square.
Okay.
Good. Okay. Just want to mention briefly the connection with list learning. Okay, so maybe you notice this connection that we used, the list function in this work. So list learning, we initially introduced it in the context of the pack characterization. It has also turned out to be this kind of efficient or useful tool for different algorithms like the one I just described. And it has also kind of led to its own line of research in different contexts sense, for example, online learning, regression, etc. So we were thinking in this work, what's the connection between list learning and weak learning? So these are two notions relating to kind of being able to learn a class in a proxy way, or mediocre way. So let me describe the connection between these two notions. Let's say I have some class H. Let's define k star to be the smallest number k, such that I can k list learn the class. Similarly, let's define gamma star to be the supremum gamma between 0 and 1, for which the class is gamma weak learnable. And here I mean the simplest notion of weak learning, just the probability of correctness is at least gamma. How are these two notions related? So what we show in this work is that in this sense, they are equivalent, they're inverse of each other. So gamma star is 1/k star. And this is also an algorithmic connection. So if we have a k least learner, a k starless learner, we can get a 1/gamma, a 1/k star weak learner, and so on. Great. Do I have 5 more minutes to?
Yeah, take it. Sure.
So I just want to briefly mention some other works that are not related to multiclass classification. So I want to talk about sequential learning. Okay. So maybe some of you know this setting of multi-arm bandits. So this is a sequential type of problem. So here we have different arms or bandits, kind of slot machines. And in each round we're able to pull an arm or query one of the slot machines. They each have some reward distribution, and we want to collect as much reward as possible. So this setting is kind of very related. I'm not going to define that formally. I want to define a slightly more general setting. So these are works with Dudik, Pacchiano, and Shapiri. So here's the setting. We have a function class f that is known to the algorithm, mapping a set of arms A. So think of these kind of slot machines, and they're mapped into the continuous interval 0, 1. This is kind of the reward. So now we're in the continuous world, and I have a target function f star in the class, and that's unknown to the algorithm. The protocol is that we continue. It has t rounds. In each round, the algorithm can query one arm, pull one arm of the slot machine, AT, and then observe the reward, which is f star over AT, maybe plus some noise. We have one of two goals. So the first goal would be just to maximize, get as much reward as possible, or find the slot machine with the most reward. So maximize f star with minimal queries. That's the first goal that we might care about. And the other one is getting sublinear regret. So regret is the gap between the best possible reward we could have collected if we knew the best one all along, minus the expected cumulative reward we've collected along the way. Good. So what we show here, first I want to talk about the setting and what it captures. So I already told you it captures multi-arm bandits, kind of a well-studied setting. In this case, the set A, set of arms, is typically thought of as finite or maybe a subset of RD, and the class F is maybe linear or smooth or simple in some sense. So I'm removing those assumptions. I don't want to think about it that way. I have a general class and a general set of arms. Another setting that we capture in this setting is in this formulation is a seemingly very unrelated setting. It comes from binary classification called statistical queries, also very well studied. In this case, the set of arms A is a possibly infinite set of binary functions H. So in this problem, we have an interaction between, you can think of it as like a student and a teacher. The student would be the learning algorithm, the teacher would be kind of the environment. In each round, the algorithm queries for some function that it thinks is the correct one, and it gets the expected error of that function, or expected gain if we're thinking of the word. Okay, so we kind of capture both of these settings in our formulation, and we want to bound the number of queries you need to make. So what we show in this work, we introduce a complexity measure F that we call the dissimilarity dimension. This is kind of a combinatorial dimension in the spirit of the VC dimension and the other ones that I mentioned. I'm not going to define it. I just want to give the intuition of what it does. So it's the size of the largest sequence of functions that are dissimilar in some sense. A bit more formally, we say that a sequence of functions f1, 2, for fd is dissimilar if for I smaller than j, the optimum of fi is suboptimal for fj. Okay, the main result that we get here is that if a function class f has a bounded dissimilarity dimension, then we can essentially satisfy both of the goals that we want to satisfy. So first, we show that polynomially in D many queries suffice to maximize any function in f. And the second goal, we show that we can get linear regret. Specifically, we get square root t up to d to 1.5. Okay. What about the other direction? The lower bound. So what if we can satisfy those goals? Does that mean that the dissimilarity dimension is bounded? So in the first setting of statistical queries, the answer is yes. So we get statistical query learning if and only if similarity is bounded. And for those who are familiar, there's another dimension called the SQ dimension. They are not equivalent, but they scale together, the SQ dimension and the dissimilarity dimension. For banded learning, unfortunately, the answer is no. So there are examples where you can satisfy these definitions, these kind of goals, but this similarity dimension is not bound. Okay, so then we go out and check what are other dimensions that people think about or usually use in this context. So maybe one of the most well-known dimensions in this context is called the eluder dimension, defined in the context of banded learning, also has extensions to reinforcement learning, very well, very kind of standard things. What we show is that the eluder dimension actually suffers from a similar problem. And specifically, we show that there are simple classes F that are easy to kind of learn, but they have a bounded dissimilarity, a constant dissimilarity dimension, but their eluder dimension is infinite. So in that case, using bounds that we give based on the dissimilarity dimension are more significantly lower. Good, but we still know that the dissimilarity dimension is not useful either. So this brings up the question of, okay, maybe not this and not neither of these dimensions is good. Can we come up with some other combinatorial dimension that captures banded learning? And by combinatorial dimension, I'm following a definition by Ben David et al., very kind of simple definition, and all of the dimensions in learning, VC, DS, Littlestone, all dimensions you can think of satisfy this. What we show in a recent work, we proved that there's actually no combinatorial dimension that can characterize banded learning in this context. So that means we need some sort of relaxed, more relaxed setting, so that we can then approach the problem.
Can I ask one question? What do you mean by combinatorial dimension here?
Yeah, so the definition is as follows. So you have usually in all these combinatorial dimensions, there's some notion of shattering, right? So you have a finite set of data points, and you have a finite subset of the function class that has some behavior of shattering, right? So in VC, you get all 2 to the combinations, and DS, you have these pseudocubes, et cetera, et cetera. But this is essentially the definition. You have a finite set of points, finite set of function, this behavior of
Some pattern.
the finiteness of the
It's a
crucial.
sub matrix of the big matrix of. Okay.
Because if we don't restrict to combinatorial, then of course there is some.
Yeah.
For each problem, I can assign the complexity.
Yeah.
You don't know how to characterize.
Yeah, but then it's kind of a philosophical question of what is the dimension of the use of it? Yeah.
So combinatorial really means,
So there's this definition.
Combinatorial, yeah. I guess
It's only the shattering.
Yeah, the notion of shattering, but essentially the key part here is that there is a finite set of points.
Similarity dimension is combinatorial.
Yes. The similarity, also the eluder, VC, fat shattering dimension, Littlestone, any dimension you could think of in learning theory. That's how it is. Question. Yeah.
What about talking dimension or universal classes? Well, can you do the dimension is right?
No, we always have the, yes. Sometimes they're equivalent, sometimes they're,
I have a general question, not related to this. When you talk about least learning,
yes.
would it make sense to develop a theory about the ordered least learning? Well, because in practice.
Some sort of ranking, you mean, like ranking, yeah, definitely, yeah. Maybe there are, I'm not that familiar, but yeah, definitely.
A stupid question. What full information case, not bench, I see everything. Then it's is combinatorial dimensions that characterize the online learnability.
So but there you have little dimension.
I mean, here you got some binary law, right? The words can be.
Yeah, I mean, so what this when I say banded learnability, I'm thinking of the best R identification. When you have full information, there's no real notion. This problem is not very well defined. What is the best R? When you know everything, it's not very challenging.
So you don't know. You know only when you see.
Okay, let's think that we